Good evening to all. I'm Sandhya, a research scholar from IIT Kharagpur. Today we would be discussing about the 8 weeks live session. The contents include initially we will be discussing about the assignment 7 questions, followed by the summary of week 8 lectures that has been studied, and we will also solve few numerical questions in regard to the week 8 lectures. So if you look at the week 7 assignment questions, the first question was the storage stability in polymer modified bitumen can be improved using. So usually we confirm the storage stability of polymer modified bitumens because after adding these polymers into the base binder, at any case, we do not want that polymer to be separated from the base binder. We want it to be completely in reaction with the base binders. So in order to maintain the storage stability, as we have already discussed in the last class, we use sulfur. And in the second question, addition of an elastomer in the bitumen is expected to. So here the question is, if we add the elastomer to the base bitumen, what is the change in the properties of that bitumen? Either will it increase or decrease the phase angle, or will it change the storage stability or specific gravity? So whenever we talk about the elastomers they increase the elasticity of the binder. So if we discuss about the phase angle, so if we remember, so phase angle usually ranges from 0 to 90 degrees. So when its value is lesser, that implies the binder is elastic in nature, and when its value is more or near to 90 degrees, we can say that the binder is viscous in nature. So here if we keep adding the elastomer to the base binder, its elastic properties would be increased, thereby its phase angle will be reduced. This is a direct question. For a dense graded cold mix asphalt, the following emulsion should be used. So we use the SS2. So what are the functions of emulsifiers? So why do we need to use the emulsifiers? Let us say when we take the base binders, initially we keep them in the blender and we make them into teeny particles and that would be suspended in the water. But we wanted that to be maintained, so that we use the emulsifiers. So these emulsifiers will create the charges on the surface of this broken bitumen particles and maintain the emulsion phase. So these emulsifiers they reduce the interfacial tension. Yes, correct. And also they prevents the coalescence of the droplets. Yes, they actually prevent the flocculation of the broken particles of the base binder. Thereby they influence the setting rate and adhesion. So all of the above. Storage silo is used for. So storage silo is a container, if you could remember. In these containers, we usually store the bituminous mixture after mixing is finished in the plant. So option D. In a batch mix plant, the aggregates and bitumen are mixed in. So usually we have aggregates separately and the bitumen separately. So and when they have been transferred to particular place to mix in the plant especially, so this mixing is taken place usually in pug mill. For aggregates having water absorption of 1%, the time period required for conditioning loose asphalt mix before the compaction is. So based upon the water absorption of the aggregates, after mixing the aggregates with the bitumen, usually we keep them in the oven at compaction temperature for conditioning, and we expect that during this conditioning period, aggregates would be absorbing the bitumen. So if the water absorption of the aggregates is less than 2%, it is always recommended to use 2 hours, and if the water absorption of the aggregates is more than 2 hours, 2%, then we can go for 4 hours. So in the current scenario, the water absorption is given as 1%. So when the water absorption is 1%, we can actually go for 2 hours of conditioning. So the option would be 2 hours. If we come to the 8th question, cold feeder bins are used for. So cold feeder bins, if you could have remember, so in the batching plant, in the initial stages, usually we store the aggregates at these cold feeder bins. Once after storing, then using the conveyor belt, we will be proceeding for the mixing in the plants. So these cold feeder bins are used for storing the mineral aggregates. Which of the following cannot be measured in the laboratory? So one of the major limitation in the laboratory is we cannot usually calculate the effective specific gravity. We can calculate the bulk specific gravity and we also can calculate the apparent specific gravity. The reason why we cannot calculate the effective specific gravity is we cannot understand how to determine the absorption of the binder into the aggregate. We do not have any experimental setup to understand how much bitumen that is being absorbed by the aggregate. If we do not understand the absorption of the bitumen experimentally, then we cannot calculate the effective specific gravity. Therefore, the option is C. So, if we come to the 8th week lectures, so in these lectures mostly the detailed discussion about all the volumetrics have been discussed, and the discussion with the introduction of the calculation of bulk specific gravity, theoretical specific gravity are the initial discussions. So, if we see about the GMB, which is nothing but the bulk specific gravity. So once after preparing this compacted asphalt mixture specimen, which is a cylindrical specimen of, let us say if it is Marshall 63.5 by 100 mm in size. So we need to determine the bulk specific gravity of this mixture. So if I prepare the specimen for dense graded mixes, as you can see here, we can actually use the method based upon SST. And if we prepare a specimen of open graded or gap graded where the voids would be more, then we usually go for this paraffin coating method. The difference would be, so if we look at the SST based method, so in the dense graded mixes, the surface would be more smooth compared to the gap graded mixes. So when I dip that specimen into the water, because I need to understand the weight in water of that specimen, when I dip that into the water, there is very less chance that water would be entered into the pores of the specimen, because finally our aim is, if we have the specimen, what is the volume of this specimen? So we wanted the volume of this specimen because it is not a regular shape and it has the irregularities on the surface. We cannot directly calculate the volume of this specimen. That is the reason why we are using this method of calculating the weight in water. In calculating, so for dense graded mixes there is no problem. We can calculate the weight of this specimen in the air, and also we can dip this specimen into the water and measure the weight in the water. Once after measuring the weight in the water, we can take that sample out and we can take a cloth and we try to wipe the surface of that specimen. That means we are actually removing the water that is present in the specimen. That is called as saturated surface dry condition. So whatever the water that is inside the specimen, let it be there, but the surface would be completely removed. That weight is called as SST. So once we know these three measurements, we can directly calculate the bulk specific gravity of the mixture. But if we take any of the gap graded mixes, as you can see here, they all have more surface voids. So you can see there are more irregularities, more surface voids. So there is a higher chance that this surface is not uniform. So when you dip into the water, there is more chance of water entering into the specimen also, which will not give the accurate measurement of the volume. So in those cases, one of the method is we need to seal entire surface of the specimen. So if the surface is completely sealed, then when we try to take this weight in water, the water will not be entered into the air voids or the spaces of this specimen. So this method usually we call it as paraffin coating method, and the first method we call it as saturated surface dry method. In addition to these two methods, there is another method called as vacuum sealing method. So in this case, what we would be, this can be applied for both dense graded mixes and also for gap graded mixes. You can see the specimen, we place the specimen into a polythene cover, and we try to apply the vacuum and seal the cover here. Once the vacuum is applied and sealed, this specimen is completely free of air voids. That means now this is all the air voids have been completely removed. Now we can directly take this specimen along with this polythene, and we can keep it in the water and take the weight in water. So if you could see here, so we have designated formulas to calculate the GMB. If you use a vacuum sealing method, dry weight in air, so initially we take the dry weight in the air, then sealed mass, that is this mass, then this sealed mass we place in the water and calculate that weight. So we already got that sealed mass in water, then dry mass in air, and specific gravity of this polythene bag. And if we come to the paraffin coating method, dry weight in air. So initially before coating this wax, we can calculate the dry weight that can be measured. Then paraffin coated mass. Once after that, we dip this into the liquid or melted wax, and we coat the specimen completely so that nothing will be entered into the specimen when we dip into the water, and we take that weight. Then the specific gravity of wax is required for this calculation. If we know this, then we can determine the bulk specific gravity of the asphalt mixture. So bulk specific gravity of the asphalt mixture, when I discuss, this contains aggregates plus bitumen and also plus air voids. So this is a mixture of these three. If we have only aggregates and the bitumen, that means only the solid particles, what is the specific gravity of that loose particles, loose mixture? So to calculate that, we usually call that specific gravity as theoretical specific gravity or GMM. So we have a method. One method is we can also use the Corlac method, which we have used for calculating the vacuum sealed method for this compacted bituminous mixture. We can use the same method for this the calculation of theoretical specific gravity also, but that always requires a higher amount of loose mixture to be prepared. So in addition to that, using the same concept, we can also go for this pycnometer method. So what do we do in this pycnometer method? So we take a pycnometer, we fill this pycnometer with water, and we will take the reading pycnometer plus water. Then again we will take the pycnometer. In this pycnometer we will fill the loose asphalt mixture. Loose asphalt mixture means we take a particular amount of aggregates and we add a certain percentage of binder and we mix, and we keep in the conditioning for at compaction temperature for 2 hours. Then we take it out. After taking that out, we try to spread that loose mix on a surface, because we wanted all the material to be separated. We do not want any flocculation. So we try to separate when it is hot itself, because it is completely difficult to separate when it becomes cold. So after separating that, then we will place them into this pycnometer, and we will fill some water to the level of this loose mixture. Then we apply the vacuum here, we remove all the air bubbles, and we also apply the vibrations if required. Then after that we will fill the water till the top, then we take the measurement. So these are the two that are required to understand or calculate the theoretical specific gravity of loose mixture. So what happens when you keep adding the binder content to this GMB and GMM? So this is actually GMB versus binder content. So initially what happens? Initially we try to add bitumen content. Initially there was a particular amount of bitumen content. you have aggregate, you have added let us say 4% of bitumen content, then this bitumen will be acted as a lubricant in between the aggregate particles. When it acts as a lubricant, it tries to reduce the friction between the aggregates. So when we try to mix and compact, it is easy for us to get compacted. So if you thereby density, let us say initially there was some density GMB. If I keep adding more bitumen, the lubricant would be more, thereby the workability will be easy and the mix gets compacted more easily and the density would be increased. So if we keep adding the bitumen content, till particular amount of bitumen content, the density would be increasing. After particular amount of bitumen contents, if you add the bitumen into this aggregate mixture, so there are aggregate particles and in between there is a bitumen. So what happens if the bitumen amount is more? So bitumen will be more and it tries to keep the aggregate particles apart. That means usually bitumen's work is it should make the aggregate particles to come closer and also make the compaction easier. But here if you keep adding more bitumen, it will try to separate the aggregate particles to far distance. So then what happens? It will not get compacted well. Thereby the density starts decreasing. So after particular amount of bitumen content, you can see that the GMB would be decreasing. But unlike the trend of the GMB, if you could look at the GMM, the theoretical specific gravity of loose mixture would be reducing with addition of bituminous content. So if you take the initially loose aggregate particles and if you try to add some bitumen, so they try to compact better and in the same way what happens as you keep increasing this bituminous content, volume keeps increasing. Whenever this volume keeps increasing, what happens, the percentage of stone aggregates gets reduced but the volume is increasing. So when the volume keeps increasing, in the specific gravity value will be reducing. So these are the two trends of GMB and GMM. And this is a phase diagram for the volumetric parameters. So if we could see, this is our bituminous mixture which contains aggregates plus bitumen plus air voids. So if I separate them into the individual phases, this is the aggregate and this is the amount of binder that is being absorbed by the aggregates. After getting absorbed, then whatever the bitumen remain, that will be on the surface of the aggregate and we call that as effective bitumen. After that also being covered over the surface, whatever the air voids that are left, that we call it as air voids. So this air voids plus total bitumen is nothing but the combination of effective bitumen plus the absorbed bitumen and this aggregate volume all together is called as total volume. So let us discuss about few of the volumetric parameters that are very much useful in the mix design. The first volumetric parameter would be VMA, voids in mineral aggregates. If we look at the phase diagram here, this is the aggregate and this is the absorbed bitumen and after this absorbed bitumen, so these two together, aggregate plus the absorbed bitumen would be called as bulk volume of the aggregate. Because if I take the aggregates and if I add some amount of bitumen, let us say some amount of bitumen is being absorbed by the aggregate. That means that bitumen is actually placed in the pores of the aggregates. So that is a part of aggregate now. We can call that volume as bulk volume of the aggregate. So beyond this, whatever the bitumen that is there, that is actually covering the surface of the aggregate. That is not the part of the aggregate. So the amount which I have shown here, which consists of, this is the effective bitumen and this is the air voids. So this volume is actually called as VMA, voids in the mineral aggregates. So voids in the mineral aggregates is volume of voids, which is nothing but this volume of voids plus volume of effective bitumen. Volume of effective bitumen is this. These two volumes together is called as VMA. And we also have seen the detailed derivation of this, how to arrive from this to this in the video lecture. So we can rewrite this VMA in terms of bulk specific gravity of mixture, bulk specific gravity of aggregate, and percentage of binder content in the mixture. If we further discuss about this voids in mineral aggregates, so if we could see the image here, on the y-axis this is VMA, and the x-axis this is the binder content. What happens is, so the code recommends that we should have a minimum VMA. That means VMA, some percentage of VMA should always be present in the asphalt mixtures. So when I say minimum VMA is required, that means minimum gaps or spaces are required so that I can actually place some amount of bitumen, and I can also have some amount of air voids. So in order to accommodate this bitumen and also to accommodate few air voids, I should have this VMA minimum. So whatever the VMA behavior we observed in the mixed design, first thing is it should satisfy the VMA minimum. Here in the diagram, the red color line which I have drawn here shows the VMA minimum. And if we see the other curves, this is the 1, 2, 3, 3 VMA curves. Out of 3 VMA curves, the curve 1 actually satisfies the VMA minimum. That means if you see here, if the VMA minimum is this, if your curve is like this, that means this is the binder content. At all the binder contents, you can see that VMA is above the VMA minimum. That means that is actually satisfying the criteria. But if you see other curves, which is 2, what happens? At this is the minimum. So there are locations you can see that the VMA is actually lesser than the VMA minimum. That means this curve has more sensitivity. And if you see this curve also, you can see VMA values are lesser than VMA minimum. So one would be more desirable. This shape actually called as flattened U shape. So when we have 3 different kinds of yes sir, you can unmute and ask sir.
Madam, why it is that the VMA should minimum VMA should be always less than this? Why this diagram? I didn't got it actually.
Okay.
And what is this 14% you written?
That is, for example, if they have mentioned VMA minimum as 14, that can be 14, 12 or anything. So, for example, this VMA is actually to accommodate air voids plus bitumen. So,
yes.
if I don't maintain this minimum, let us say if I don't say that minimum 12% of VMA should be there, people can actually create the bituminous mixtures with 10%. Then in the 10%, it may or may not be possible to accommodate the place for bitumen and also air voids. So, in order to have minimum...
Madam, VMA is only the part of the bitumen that is absorbed by the aggregate. That is the VMA, na?
No, VMA is actually, if I can show this phase diagram. So if you come here, sir, this is VMA, the top 4.
VMA means bitumen plus air voids.
Effective bitumen plus air voids. So this always should have some minimum amount of space should be available so that we can...
But that here you VMA you have written volume of voids. Acha, volume of voids. Correct.
So
yes, ma'am.
Volume of voids plus volume of effective bitumen out of total volume. So we should maintain that VMA.
VT is total volume of the specimen.
Yeah, total volume. So out of this total volume, we should have this much VMA.
Okay. Please proceed, ma'am.
Yes, sir.
Hmm.
So this VMA minimum should be maintained so that we can able to accommodate air voids of 4% whatever we are aiming for, and also the amount
Hmm.
of bitumen that is required to actually coat the aggregates. So if you see three curves here, the first curve actually satisfies the VMA minimum and also has less sensitivity. Let us say if you have VMA curves like this, two VMA curves, this is the flattened shape and this is also flattened shape. But there are times where if the change in the VMA with binder content is very more, that means that curve is actually more sensitive to the change in bitumen content. We do not want our VMA to be more sensitive to the change in the bitumen content. So we need to select this curve in such a way that it should satisfy the VMA minimum and also should not be more sensitive to the bitumen content. So in addition to
Means
the
VMA should be constant. Means somehow it is should be constant.
VMA will not be constant, sir. With bitumen content, it will be changing like flattened U shape.
Okay, okay, okay. Means initially it is increasing. After then it is no. Initially
Initially,
it
it
is
will
decreasing.
decreasing. After particular bitumen
Uh,
content, it will be increasing.
increasing. Okay.
So initially it will be decreasing because it is exactly like the
Oh,
GMB how we have discussed. So as I keep adding bitumen content, what happens? Let me erase this. Let us say in the VMA we have some voids now. So these are the air voids and here bitumen is filled. So if I keep adding bitumen, what happens? These air voids will be filled slowly. So when I keep adding the bitumen, air voids will be reduced and the mix will be compacted, and you can actually see the VMA would be reducing. Initially, let us say voids would be more. Then as you keep adding the bitumen, you can see the VMA would be reducing. After particular amount of bitumen content, if you keep adding more bitumen, what happens? That bitumen amount, the volume of the bitumen would be more in such a way that it will make the aggregates to move apart, and that thereby it actually increases the total volume, which is nothing but the VMA volume. So if we select any of our binder content on higher VMA side, that means on that side actually there is higher amount of bitumen content, thereby there is a problem of bleeding and rutting. And as far as compaction effort is considered, let us say in the Marshall mixed design, let us say we are choosing 75 blows. So this 75 blows corresponding to the, let us say if the traffic is greater than 1 MSA, usually this Marshall has come around 1990s. So during that time, we do not have the traffic like more than 100 MSA like today's traffic. So when the traffic is more than 1 MSA, they have suggested to go for 75 blows. If the traffic is less than 1 MSA, they also have recommendations for 35 blows, 50 blows corresponding to the traffic. So what will happen if I design for wrong blows? So if you could take this, this shape, this curve, on y-axis this is VMA, on x-axis this is bituminous content, and you can see this is one curve, this is another curve, and this is for 50 blows and this is for 75 blows. Let us say I have designed a mixture for 50 blows, but in field what happens? I have come across 75 blows. That means I have assumed that my traffic is 1 MSA and I have designed, but in the field it has happened that traffic was doubled, or let us say 100 MSA has come. What happens then? Let us say we have a sponge and we have dipped that sponge into the water, and if I press little, and I also assume that nobody will press that sponge too much, so everybody is pressing with little pressure. But if somebody presses more, then what happens? More amount of water would be coming out. In the same way, we expected that the traffic would be less, so we designed for 50 blows. But in the field, if you get more traffic, that means that is coming onto this 75 blows curve. Then what happens? The bitumen content might be on the dry side when you design for 50 blows, but when it comes to this 75 blows, it will come to the wet side because you are applying more traffic, then you are compacting more, thereby the bitumen content would fall on the wet side. When it falls on the wet side, there is a problem of bleeding, bitumen would be coming out. And what happens if I design for higher traffic? That means in the field only 50 blows will be coming. That means lesser traffic will be coming. But I have designed it for 75 blows. Then what will happen? Let us say I expected that 1000 vehicles will come, but only one vehicle has come. Then what happens? Whatever the compaction I am expecting, that compaction will not happen. Then all the air voids will be remained as it is. Then air voids are more. What happens? There would be a circulation of more air into the in between the aggregate particles. Thereby oxidation of bitumen can happen and the mix will be becoming brittle and there is a chances of water and moisture damage. So the selection of compactive effort plays an important role as much as like VMA. And in addition to this VMA and compactive effort, there is another volumetric parameter which is called as VFB, voids filled with bitumen. So if we could see here, this is our VMA. That means this air voids and also this effective bitumen together is called as VMA. So in this VMA, if we could observe, this much amount is filled with bitumen and the remaining are the air voids. So I wanted to understand out of this total VMA, how much amount is actually filled with bitumen. So voids filled with bitumen, that is called as VFB. So if we come to the equation, VFB is equal to volume of the effective bitumen, that means this number 1 divided by volume of voids plus volume of effective bitumen. Volume of voids is this plus volume of effective bitumen is this. So out of this total VMA, so what is the percentage of effective bitumen that is filled? So we can also rewrite that as you can see here, volume of effective bitumen is nothing but total VMA. Out of total VMA, if I remove the air voids, you will get the effective bitumen and the divided by VMA. So this VFB, if you could see the equation, this VFB actually depends upon VMA and also air voids. So we usually do not need to bother about the VFB, but the code suggests that we should have a range of VFB. That means minimum it should satisfy this much and maximum it should satisfy some amount of the percentage. Why does it says that is, let us say if I do not restrict my VFB, let us say here the code suggests that VFB should be 65 to 75%. That means if I have this much total VMA, maximum 75% of VMA should be filled with bitumen. Beyond that we should not fill. What happens beyond that? If that fills, then most of the percentage of the VMA will be filled with bitumen and you will have very lesser air voids and the bitumen would be very much high. Yes, sir.
How one can ensure that this 65% to 75%, how one can ensure it that effective filled vitamin is 65 70? How we can ensure, how can we get it?
Yeah, actually, if we calculate the VMA, so usually, initially we calculate the VMA, sir, and after calculating the VMA, if we have the air voids, based on that, we will actually calculate the VFB, voids filled with bitumen. Then VFB usually actually it will satisfy the range of 65 to 75%. So for this we do not need to do anything specially. We keep doing the trials of let us say we take 5 trial grinders and we do the mixed design. In this mixed design, first we confirm the 4% air words. When the 4% air words is confirmed, we go for another check whether that is satisfying the VMA minimum or not. If it is also satisfying the VMA minimum, then based on the air voids and VMA, we can calculate the voids filled with bitumen. So when the voids filled with bitumen is in this range, we can actually confirm that the bitumen is not filling too much and the air voids are sufficient. Thereby we can also restrict the too much of binder in the mixture. So when we restrict the too much of binder, that actually creates the we are actually avoiding the tender mixes or the bleeding in the bituminous mix. So when we have this initial volumetrics like GMM and GMB, based on that we can also calculate the total air voids. These air voids are actually the main parameter based on which we do the mix design, because we assume that after a particular amount of years, when the pavement is subjected to a lot of traffic, we expect that it will be getting into the stabilized state and the air voids keep on reducing, and it will reach to a constant or stable state where the air voids would be of the 4%. So we always aim for that 4% air voids and we design our mix. So to calculate this air voids, GMM minus GMB by GMM into 100, and this can also be rewritten as this, volume of voids by volume of total. So if you see a few other points to be understand, so the designed air voids will be in the range of 3 to 5%, mostly 4%, and this 4% is actually achievable after particular years of traffic and not after construction. So after the construction, we expect that the air voids in the pavement are around 6 to 8%, and we allow the traffic for the initial few years. After a particular number of years, the air voids which are present 6 to 8% will be reduced and it will be reached to around 4%, that means in the range of 3 to 5%. This 3 to 5% is what we are actually, yes sir.
Yes, but in Morth it is given that DBM should have a this 3 to 5% of ER words. So we are designing the mold in the form of 3 to 5%.
Yeah, we are designing the mixed design. So because after calculating all the volumetric parameters, so you will have bitumen contents and the corresponding VMAs. We will have bitumen contents and the corresponding GMM. We will have bitumen contents corresponding GMB. So
No,
out
what I meant to say that you are saying that should be 6 to 8%. If 6 to 8%, then compaction can be maximum of 90 to 93% only.
6 to 8% is immediately after the construction, but in the lab we actually design for 4%. So what I am here saying about 6 to 8% is, in the lab we will not design for 6 to 8%. We always design for 4%. That 75 blows which we are choosing, that corresponds to the 4% air voids. But when we do the pavement construction initially, it will have 6 to 8%. After a particular amount of years, it will be reduced to 4% of air voids. So actually we are forecasting that 4% of air void state, and we are casting that specimen, and then we will be checking for the volumetrics. So in reducing these air voids, so one of the thing to be remembered is the air void should not be less than 2%. So when the air voids are too less, it may lead to the rutting. Air voids are too less means binder must be too high. When the binder is high, mix could be very soft. And another thing is air voids should not be more than 5%, which may lead to the brittleness, because when the air voids are very high, there is a higher chances that there is a circulation of air which will cause to the oxidation of the binder, thereby the more stiffening of the binder leads to the brittleness of the mixture and premature crackings and stripping and moisture damage. All other cracks has a possibility. In addition to these points, dust to binder ratio, when I say dust, dust implies the any amount of the material that is passing 75 micron. So that is the dust, and we already have a bitumen content. So this dust actually being very fine material having more surface area, it has the ability to actually absorb or take more bitumen content. So we need to make a concentration on this dust to binder ratio to keep in the range of 0.6 to 1.2. What will happen if the dust is very high but bitumen is very less? then you will not have the sufficient bitumen. And if the dust is very less and bitumen is very high, then you will be having the very soft mixes. So we try to maintain this range in the range of 0.6 to 1.2. So in the end of this week 8, so we have also discussed about the summary of Marshall and also super pave. So in the Marshall mix design, before doing the mix design, usually we check the aggregates for all these physical properties like impact, Los Angeles abrasion, soundness, flakiness elongation, water absorption, and of course specific gravity. But when we do using super pave mix design, there are two types of properties that need to be checked. One is the consensus properties. These are the properties that are mandatory to be satisfied by the aggregates. So before using the aggregates, all these consensus properties should be satisfied. Then only we will select the aggregates for the mix design. And these are the source properties. These are complementary tests that needs to be performed on the aggregates. So this coarse aggregate angularity, fine aggregate angularity, because we want aggregates to have a certain amount of angularity, so that when I compact, they should have better interlocking. So these two properties are related to that. And regarding all these tests, we already have discussed in the initial lectures, where the flatness and elongation and the clay content. So we also have done sand equivalent test to understand the clay content. And if we come to the source properties, it includes the toughness, soundness, and deleterious materials. But if you see the Marshall, we do not have anything like consensus properties or source properties. Whatever we have are all these preliminary aggregate tests. As I was discussing previously, so we already know that we are using 75 blows which corresponding to the more than 1 MSA. But if the traffic is lesser than that or in this range, 35 or 50 are recommended. But in the current scenario, for all the reasons, we use 75 blows because the traffic is always more than 1 MSA. So in regard to this week 8 lectures, let me solve few questions. The first one is paraffin coating for determination of bulk specific gravity of bituminous mixtures will be required for which of the following mixes. So as we have discussed, we discussed about three types of methods to determine the GMB. Yes, option C. Yeah, option C is correct. But in addition to the option C, if you could observe, there is option B, which has open graded mixtures. That means this also have more air voids like gap graded mixtures. So both option B and C both will be requiring paraffin coating method. So option D is the correct. And if I come to the second question, the optimum binder content of bituminous mixture is found to be 4.5. That means OBC is given as 4.5%. Bulk specific gravity of mineral aggregate. So GSB is given as 2.750, and bulk specific gravity of bituminous mix also given. That means GMB is given as 2.412. Calculate the value of VMA. So we know that for calculating the VMA, one is volume of voids plus volume of effective bitumen divided by total volume. In addition to that, we also have another formula involving this GMB, GSB and bitumen content. So if you could see, so this is the another formula where which involves GMB, GSB. So if we could able to substitute there, then VMA would be 1 minus GMB is 2.412 divided by 2.750 into 1 minus, what is the percentage of bitumen? 4.5 divided by 100 into 100. So if we substitute this and if we calculate, we will get the answer 16.23 as the optimum bitumen content, 16.23 as the voids in mineral aggregates or VMA. And next question is, The minimum VMA in an asphalt mix is a function of. So voids in mineral aggregates, this was also discussed previously, is a function of. So when I say VMA, that means minimum voids minimum voids are required. Why? Because if I have minimum voids, that will facilitate the place for bitumen, especially the effective bitumen. So how much effective bitumen is required? It depends upon the NMAS. So if the aggregate size is very small, then it will have more surface area. If it has more surface area, then it requires more bitumen to coat. So if it requires more bitumen to coat, then your VMA will be more. So the amount of VMA is varied based upon the NMAS, nominal maximum aggregate size. So the option C is the correct. And if we come to the fourth question, a 4% binder content. So binder content is 4%. At 4% binder content, calculate the air voids. So they are asking us to calculate the air voids. Mixture is having a bulk specific gravity of 2.45. So GMB is given as 2.450. The effective specific gravity of aggregates is equal to, effective specific gravity is equal to 2.720. Assume that the specific gravity of bitumen is 1.02. Specific gravity of bitumen is given as 1.02. Currently, they are asking us to calculate air voids. So, usually air voids is calculated if we know GMM minus GMB divided by GMM into 100. So, if we know the GMM and GMB, we can calculate the air voids. But in the current problem, only GMB is given. GMM is not given. How do we calculate the GMM? Because already effective specific gravity is given. So, if we know the effective specific gravity, there is a formula to calculate the GMM. So, if you see this equation, GSE is given, percentage of binder is given. So, this is percentage of binder 4 by 100. Specific gravity of binder is given 1.02 and GSE is given. Only unknown is GMM. So, from this equation, we can calculate the GMM. Once GMM is calculated, we can substitute GMM here. GMB is already given and we will get the air voids as 3.92. And if we see the fifth question, the desirable VMA versus binder content curve should be. So, desirable VMA versus binder content. This curve should be above minimum VMA line. That means their option is it should be above and also below or should pass through. Okay. So our VMA curve should always be above the VMA line. We know that always it should be above the VMA line. Yes. And the sixth question is 1% reduction in air voids increases the binder content by approximately. So let us say if we already have some 4.5% of binder content and a particular 4% of air voids. So if I reduce my air voids to 3%, so from the past studies and observations, there was a measurement that if I reduce the air voids to 1%, the increase in the binder content would be approximately around 0.4%. So 0.4%. If I reduce my air voids to 1%, that means then I have to add minimum 0.4% of bitumen content. In addition to that, there was also another observation is if I increase the air voids to 1%, VMA will be increased to around 0.1 to 0.2%. Which of the following is a consensus property in the Marshall mixed design process? So they have given that in the Marshall mixed design, what is the consensus property? Is it the impact value? Is it the fine aggregate angularity or the deleterious materials or none? So if you could remember, these consensus properties or source properties are actually part of superpower mix design. In the Marshall mix design, there is nothing like consensus properties or source properties. So usually the option is none. If the volume of air void in the bituminous mixture is 4%, so air void is given as 4%, volume of bitumen is 12%. So volume of bitumen is 12% and the volume of absorbed bitumen is 1%. Volume of absorbed bitumen is 1%. Calculate the value of VFB. So what is the value of VFB they are asking. VFB is nothing but voids filled with bitumen. So how do we get the voids filled with bitumen? This is the volume of the effective bitumen. This is volume of effective bitumen divided by VMA. So out of total VMA, how much is the effective bitumen volume? That is what we call it as VFB. But how do I get the effective volume bitumen? I know total bitumen is 12%. Out of this 12%, 1% is absorbed by the aggregate. So whatever is remained will be effective. So that would be 12 minus 1% divided by, how do I get the VMA? VMA is nothing but air voids plus effective bitumen volume. So what is the air voids? 4% is the air voids. What is the effective bitumen? Just now we calculated. Effective bitumen is nothing but total bitumen minus absorbed bitumen, that is 11%. So VFB would be 11% divided by 4 plus 11, that means 11 by 15 into 100. So it would be around 73.3%. And if we see this question, if a bituminous mixture is to be produced with 4000 grams of aggregates, so aggregate weight is given as 4000 grams and binder content is given as 4.5%. The weight of the binder to be added should be, so weight of the binder they are asking us to calculate. So when they say 4.5% is the bitumen content, that means that is 4.5 by 100. That means 4.5 percentage of bituminous mixture. So bituminous mixture means aggregate plus binder. But in the current problem, aggregates are given. How much? 4000 plus, but binder is not given. X, we don't know. So 4.5 percentage of that mixture, 4.5 percentage of this, 4.5 percentage of this total mixture will be some binder content, again X. So this we can now calculate. So 4.5 into 4000 plus X equal to 100X, thereby 4.5 into 4000 equal to 100 minus 4.5x. Okay, if we calculate this, so if we calculate this, we will get the answer as 188.5. So these are the few questions based upon the last week lectures. And if there are any questions, you can comment under the video also, I can reply. And you can see this recorded video, we will share the link. Thank you. Okay, then I am closing the meet.